So let's move forward with complexity and self-organization. The next crucial manifestation of complexity for us to understand is self-organization. Remember that the structure of complex systems is not imposed on them, but just emerges in the local interactions between their elements. Structure is the result of action in the system, not something that has to exist in an a priori fashion. However, this fits poorly into our intuitive worldview, which predisposes us to assume that someone must have arranged the elements in a particular order when confronted with something organized. So every time we see something so well organized, you think it must be a design element. We are generally inclined to attribute it to some mysterious intelligence if we cannot identify anyone responsible for the seemingly peculiar organization. So these are often called teleological, but I don't want to get into some inaccurate example now. Nevertheless, the organization of complex systems is not the makings of some external or centralized authority, commander, controller, coordinator, or creator. It's the result of self-organization, which is the appearance of structure or pattern without an external agent imposing it. So you put together the elements, you link them, they start interacting, and a self-organized pattern emerges that you didn't even imagine. The elements may have varying influence on the structure and functioning of the system, and there may even be observable subsystems for coordination or control. For example, the brain and central nervous system of an organism, and the CEO and line management of an organization. Yet the actual organization of activities and events in complex systems are overwhelmingly self-organized. So it is order for free in Kaufman's words. Centralized control may have some advantages, but at some level it must itself be based on distributed control, and fully centralized control means the system loses its adaptability and survives only as long as the environment is stable. So if you're fixed in your organization and respond in one way only, and the environment in which you live changes, like climate change, then you may become vulnerable to this change because your self-organization is not adaptive enough to the changing situation, right? So here is a self-organizing shoal of fish moving as one, and often they organize into this because they are able to confuse the predators by doing this. So if you have dolphins that are, you see many examples of bowls of fish forming that keep moving together, or swarms of birds or midges that form very fascinating patterns that seem to move together, and often there are very good mathematical models to explain how this self-organization happens. So there are purposes to it, and they are evolved to happen to achieve some purpose in terms of complexity and self-organization, like confusing predators. In technical terms, the second law of thermodynamics stipulates that disorder or entropy can only increase in any system left to itself. So you typically talk about a closed system which keeps going towards increasing entropy by the second law of thermodynamics. Although this is a fundamental law of our universe that is impossible to break, it does not preclude increasing local order as long as the total disorder is increasing. So you can see that each fish is by itself not so well organized, and can be in fact moving as if it's trying to increase dissipation of energy and increasing entropy, but locally they can get organized, and overall if you take the system that contains it, then the entropy must still go up. Okay, so this prospect for local order is relatively straightforward to grasp in the case of self-organization towards equilibrium. If looking at the example of crystallization, the increase in the order of crystal, which looks like decreasing entropy, is compensated by increasing disorder of the liquid the crystallizing molecules were dissolved in. So that's increasing entropy, resulting in a total increase in disorder of the crystal and the liquid together until equilibrium is reached and everything stops. So that's death. Earth. So I'm moving, making organized movements. I'm saying things, words that are organized into coherent patterns, but I consume energy from different sources and I convert it into coordinated motion. So even though locally I'm ordering myself into doing things, moving my hands and saying things that form patterns, the overall entropy goes up. So I am increasing entropy as well, and you are doing the same. The combined entropy or disorder of a system and its entropy can only increase over time. This gets discussed in the context of Big Bang, the expansion of the universe, and what happens as the universe keeps expanding. Will there be a big crunch, or will it just go into a diffuse blue light with entropy that will make it impossible to organize it back together, and so on and so forth. Reading a little bit more here, we also tend to ignore complexity when we attempt to explain unexpected events. So that's 9:12. Did I jump things? This is 9:11. So Singapore has a typically tropical climate with the lowest recorded temperature of 19.4 degrees centigrade. We'll come back and see what that is all about. This is 9:12, a sign commemorating the 3 Mile Island nuclear accident in 1979, which is being discussed in the context of explaining unexplainable events. So this nuclear accident at 3 Mile Island became a poster child for the early nuclear accidents. Of course, we have had Chechnya, what's the Russian one? Suddenly it escapes my mind. And we had the Fukushima disaster on March 28, 1979, and for several days thereafter, as a result of technical malfunctions and human error, 3 Mile Island's Unit 2 Nuclear General Station was the scene of the nation's worst commercial nuclear accident. Radiation was released, a part of the nuclear core was damaged, and thousands of residents evacuated the area. Events here would cause basic change throughout the world's nuclear power industry. So even as I'm reading this, my brain was working trying to remember the Russian nuclear accident, and that's Chernobyl, which of course created lots of dangerous radiation levels across the world. And now we look at Chernobyl as a site where life has returned and life is getting organized again. So we need to observe it longer to understand how these complex events happen. So when we are faced with unexpected occurrences, especially when they have catastrophic results like a nuclear accident, we tend to ascribe their causes to a rare combination of unlikely circumstances. Something happened with the plant, the human beings didn't respond correctly, safety measures were not followed, and so on and so forth. In the case of Fukushima, you had the we discussed this in the disasters. There was a earthquake which caused the tsunami. The tsunami inundated the nuclear plant, and then nuclear accident happened. Does seem like a combination of unlikely circumstances. So when you have to explain the crash of the stock market, an earthquake, or the sudden outbreak of political violence, we try to find a number of factors that combine to cause it, often with the hope of showing that the chances of the same combination of factors occurring again are slim. So you could call them black swan events that only happen because of such coincidences. But this is the emergence of complexity and self-organization when multiple elements act together. This kind of analysis, however, is the result of trying to explain the behavior of large complex systems by extrapolating from the behavior of small simple systems. Unfortunately, this extrapolation fails. Okay, so we'll come back and look at consequences of complexity in the next podcast, but you get the sense that we are going systematically through the various properties of complexity, its characteristics, its manifestations, its emergence, and so on. And we will go back then to representing the human environment system to see how we need to deal with this complex Earth system, with human beings now being a big part of the forcing to understand it, explain it, and define a preferred state from the current state which we have created, which we are not happy with because the risks are too high and growing too fast, and too many other species and large parts of humanity itself are not in a good position. So we need to come back and think of these concepts in the context of Earth system and modeling the human environment systems before we move to changing the world, to see how we can design projects and programs to achieve the desired state we want to accomplish. Okay, so see you in the next podcast.